move on to the next topic. So here are the Kirchhoff rules. Okay, now what we'll do is we'll look at something called an RC circuit. R being a resistor and C being a capacitor. So here's a battery, here's a switch, here's the capacitor, and there's the resistor. Okay, so here's the same circuit using electrical symbol. There's the battery, and you can see it's an ideal EMF source. There's a capacitor, resistor. Okay. So what we want to know is when you close the switch, the capacitor charges. What happens is electrons flow from here and collect over there, and those guys repel electrons which come over here. What you want to know is how does the current change? Okay, so this is the circuit, and let me show you the simulation of it. So here is a here's the EMF, there's the capacitor, there's the resistor. And I will close the switch, and you see the charge is building up like that. And the current in the circuit is dying out like this. Once the capacitor is completely charged, the current has gone to zero. Okay. So that's what's happening. Once the capacitor is completely charged, the current in the circuit has gone to zero. Now here's what I'll do. So again, I'll let you guys look at this graph again for these values of resistance and capacitance. Okay, so there's the capacitor being charged. Okay, it's completely charged, and so the current in the circuit has gone to zero. Okay, now what we'll do is we'll increase the resistance. And let's see how the circuit charges. And now you see it's charging much more slowly. Okay. So anyway, we want to know how does the capacitor charge. We want to know the current in the circuit. Okay. So this is what we're after, the functional form, Q as a function of time. Okay. That's what we're interested in. Now, you've learned in the past that if you want to describe the behavior, if you want to mathematically model the behavior of the circuit or a system, anything, okay, so you want to mathematically model the behavior of this circuit after you close the switch, what the mathematical model generally is a differential equation, okay? And so that's what we'll do. Okay, so here's the deal. You close the circuit, and that's when time starts. So you close the circuit, that's t equal to 0. And now you want to know what is the behavior of this circuit going forward. Okay. Now this is a closed loop, so you can apply Kirchhoff's loop rule to this closed loop. Okay. So we'll start off here. We'll go across this element, and there's plus E. Then you're going from a high to low voltage. The voltage across the capacitor is Q by C, and so that's minus QC. And then you're going with the current, and that is minus IR. Okay. Now the current in the circuit is equal to the rate of change of charge on the capacitor. Okay. So let's go to the chalkboard. Okay. So again, here's the circuit. Okay. So this is QT, and that's minus QT. Again, so that's the charge IR. Okay, again, we are starting off here and going across this element. That's E. And for a capacitor, it's C or Q or V. So the voltage across a capacitor is Q over C. And so at a given instant, so it's minus QC minus Q over C. That's the change in voltage across the capacitor. Okay. And then you're going across the resistor, it's minus IR. I as a function. Okay. So there is your equation using Kirchhoff's loop rule. Okay. So this rule helped you set up this equation. Now, see, the current is the rate of change of charge. So IT is dq by dt. Okay. So this equation becomes okay. And we'll clean this up. So dq by dt minus is plus qt by rc. So there is the differential equation that describes the behavior of the system, and you want to solve this differential equation. Okay. And there is the differential equation. Okay, so dq by dt plus q by rc equal to E by R. Okay. So here is the mathematical model for the behavior of this system, and you solve this differential equation. Okay. And you learn various techniques in your differential equation classes to solve these types of equations. Okay. One of the techniques is, I mean, you learn to make educated guesses at the solutions and so on. Okay. And you'll learn other techniques. Okay. All right, so the solution to that equation is QT is CE, C is the capacitance, E is the EMF of the battery, 1 minus e to the power of minus t by RC. RC is called the time constant of the circuit and denoted by tau. Okay. So you can see that there the greater R is and the greater C is, the greater the time constant. So here are three different curves. So there's a curve for time constant of 1 second. This is a time curve for time constant of half a second for 2 seconds. Okay. So greater the time constant, slower the capacitor charges. Okay. So anyway, there's the functional form. There's how the capacitor charges as a function of time. That's the charge and the capacitor as a function of time. Okay. You can take the derivative of that, and that'll give you the current in the circuit. And the current in the circuit decays exponentially with the same time constant. Initially, at time t equal to 0, the current is E by R. At time t equal to 0, the current is E by R, as if the capacitor wasn't even there. Okay. And because of the presence of the capacitor, the current decays exponentially. Okay, let me summarize this again. So what we did, so we're looking at an RC circuit. Here's the circuit. What we want to know is how does the current change in the circuit after you close the switch. So you close the switch and you wanted to know the behavior of the current and the charging of the capacitor. So to model the behavior of this system, you set up this differential equation. Okay. The behavior of the system is being modeled by this differential equation. And that's why you take a differential equation class. You will find that you have you run into all kinds of systems whose behaviors can be modeled by differential equations. Okay. And then you learn to solve this differential equation, and there's the solution to that differential equation. Okay. And now you know how the capacitor charges and the current in the circuit. Okay. So now we'll do the same thing. You've charged this capacitor, and now you're going to discharge it through this resistor. So again, this could be the flash bulb. So let me remind you of one of the first circuits I'd shown you. Okay. So for instance, you can close this switch. This is your flash flash bulb circuit in your camera. You close the switch, you charge the capacitor. Once the capacitor is charged, you open the switch. And now when you're ready to take a picture, you can close the switch and discharge all this energy through this flash bulb. Okay. So now we are interested in this portion of the circuit. How does this capacitor discharge through this resistor? Okay, and that's what we're going to look at. So the capacitor is charged. We're going to close the switch, and we'll see how the charge discharges. Okay, so as the charge is decreasing, dq by dt will be negative. So just keep that in mind. And the current is going through there. Okay. All right, so again, this is a closed loop. We'll apply Kirchhoff's rule. We'll start off. We'll start off here, and then when you go across it, you're going from high to low voltage. So it's minus QC, minus Q over C. Okay, so that's the voltage across it. And now, then you're going against the current. It would be minus IR, no, plus IR. When you're going against the current, it's plus IR, except that I is dq by dt is negative because the capacitor is discharging. So minus of minus dq by dt will give you a plus I. So there is the plus IR. Okay. So there is the differential equation describing the behavior of this system of a discharging capacitor through a resistor. And you can solve this differential equation again. Okay. And the solution is an exponentially decaying charge on the capacitor. So the charge on the capacitor is decreasing exponentially. And again, take the derivative of that, and that'll give you the current in this circuit. And you see the current is also exponentially decaying with the same time constant RC. Okay. So the time constant is RC. All right. So again, so we've learned a very important thing here. The behavior of physical systems can be modeled by differential equations, and then you solve those differential equations, and you can find the solution to those differential equations. And once you have the solution, you know the behavior of the system. Now, if your solution didn't actually agree with the behavior of the system, that means your model was wrong. And then so you refine your model, okay? And then solve it again, okay? So that's what's going on. All right, so now is a good time to pause, and I'll let you